Artificial intelligence goes for beginner by knowledge and information. In this video we are discussing about types of machine learning, part 1. Machine learning can be categorized into several types based on different criteria. Here are some common types of machine learning. 1. Supervised learning. In supervised learning, a model is trained on a labeled dataset where both input features and their corresponding target labels are provided. The goal is to learn a mapping function that can predict the correct output label for new, unseen inputs. 2. Unsupervised learning. Unsupervised learning involves training a model on an unlabeled dataset where only input features are given. The model learns patterns, structures, or relationships in the data without any explicit target labels. Clustering and dimensionality reduction are examples of unsupervised learning techniques. 3. Semi-supervised learning. Semi-supervised learning is a combination of supervised and unsupervised learning. The model is trained on a dataset that contains both labeled and unlabeled examples. The labeled examples provide explicit supervision, while the unlabeled examples assist in learning the underlying structure or distribution of the data. 4. Reinforcement learning. Reinforcement learning involves training an agent to interact with an environment and learn optimal actions based on feedback in the form of rewards or penalties. The agent learns through trial and error and aims to maximize a cumulative reward signal. Reinforcement learning is commonly used in robotics, gaming, and autonomous systems. 5. Deep learning. Deep learning is a subfield of machine learning that focuses on training artificial neural networks with multiple layers, deep neural networks, to learn hierarchical representations of data. Deep learning has achieved remarkable success in various domains, such as image recognition, natural language processing, and speech recognition. 6. Transfer learning. Transfer learning leverages knowledge learned from one task or domain to improve performance on another related task or domain. Instead of starting from scratch, a pre-trained model on a large dataset can be fine-tuned or used as a feature extractor for a different but related task, especially when labeled data is scarce. 7. Generative Adversarial Networks, GANs. GANs consist of two neural networks, a generator and a discriminator, that are trained in an adversarial setting. The generator learns to produce synthetic data instances, such as images or text, that resemble real data, while the discriminator learns to distinguish between the real and fake data. GANs are commonly used for generating realistic images, video synthesis, and data augmentation. 8. Instance-based learning, also known as lazy learning. Instance-based learning methods make predictions based on the similarity between new instances and instances in the training data. Examples include k-nearest neighbors, KNN, and case-based reasoning. 9. Bayesian learning. Bayesian learning uses Bayesian inference to update probabilities based on new evidence. It incorporates prior knowledge and combines it with observed data to make predictions. Naive Bayes and Bayesian networks are popular examples of Bayesian learning algorithms. 10. Decision tree learning. Decision tree learning builds a tree-like model of decisions and their possible consequences. It splits the data based on features to create a hierarchical structure for decision-making. Decision trees can be used for classification or regression tasks and can handle both categorical and numerical data. 11. Ensemble learning. Ensemble learning combines multiple individual models to make predictions. It aims to improve performance, increase generalization, and reduce overfitting. Popular ensemble methods include random forests, boosting, e.g., ADA boost, gradient boosting, and stacking. 12. Deep reinforcement learning. Deep reinforcement learning combines deep learning techniques with reinforcement learning. It involves training deep neural networks to learn representations from raw data and make decisions in a reinforcement learning setting. Deep Q networks, DQNs, and Proximal Policy Optimization, PPO, are examples of deep reinforcement learning algorithms. 13. Online learning. Online learning, or incremental learning, refers to models that can learn from streaming data or adapt to changing environments. The model learns from individual instances or mini batches of data in an ongoing manner, updating its knowledge as new data arrives. 14. Self-supervised learning. Self-supervised learning is a type of unsupervised learning where the model learns to predict missing or corrupted parts of the data. It leverages the inherent structure or patterns within the data itself to create useful representations. Contrastive learning and autoencoders are common approaches in self-supervised learning. 15. Transfer learning for NLP. Transfer learning techniques specifically designed for natural language processing, NLP, tasks. Models like BERT, Bidirectional Encoder Representations from Transformers, and GPT, Generative Pre-trained Transformer, have demonstrated remarkable performance by pre-training on large-scale corpora and fine-tuning on specific NLP tasks. 16. Active learning. Active learning involves an iterative process where the model interacts with a human or an oracle to query for labeled data. The model actively selects the most informative instances to label and incorporates them into the training set. This approach aims to reduce the labeling effort and improve model performance. 17. Semi-Supervised Generative Models. This type of learning combines ideas from generative models and semi-supervised learning. Models like Variational Auto Encoders, VEEs, and Generative Adversarial Networks, GANs, can be trained on unlabeled data to learn the underlying data distribution and generate new samples. 18. One-shot learning. One-shot learning focuses on training models to recognize new classes with only a single or very few labeled instances. This is particularly useful when dealing with rare classes or situations where obtaining large amounts of labeled data is challenging. 19. Meta-learning. Meta-learning, or learning to learn, involves training models to acquire knowledge or learn to adapt quickly to new tasks or environments. It aims to improve the efficiency and effectiveness of learning algorithms by leveraging prior experience or learned strategies. 20. Causal inference. Causal inference aims to understand cause and effect relationships in data. It involves inferring causal relationships from observational or experimental data. Methods such as causal graphical models and propensity score matching are used to identify causal effects. 21. Time series analysis. Time series analysis focuses on modeling and predicting data that varies over time. Techniques such as autoregressive integrated moving average, ARIMA, recurrent neural networks, RNNs, and long short-term memory, LSTM, networks are commonly used for time series forecasting. 22. Anomaly detection. Anomaly detection involves identifying unusual or anomalous patterns or instances in data. It is useful for detecting fraudulent transactions, network intrusions, or any unexpected behavior. Methods such as statistical approaches, clustering, and deep learning can be employed for anomaly detection. 23. Multitask learning. Multitask learning aims to learn multiple related tasks simultaneously, leveraging shared knowledge and relationships among tasks. The model learns a shared representation that benefits all the tasks and improves overall performance. 24. Federated learning. Federated learning enables training models across multiple decentralized devices or servers without sharing the raw data. Instead, models are trained locally on each device, and only the updated model parameters are aggregated to create a global model. This approach is useful when privacy and data security are concerns. 25. Deep transfer learning. Deep transfer learning combines deep learning techniques with transfer learning. It involves leveraging pre-trained deep neural networks, such as convolutional neural networks, CNNs, trained on large image datasets like ImageNet, and adapting them to new tasks or domains. This approach can significantly reduce the need for large labeled datasets for training deep models. 26. Online reinforcement learning. Online reinforcement learning combines the principles of reinforcement learning with an online learning setting. The agent learns from sequential interactions with the environment in real time, updating its policy based on immediate feedback. Online reinforcement learning is useful in scenarios where the environment or task dynamics may change over time. 27. Evolutionary algorithms. Evolutionary algorithms are inspired by the process of natural evolution. They use concepts such as genetic variation, selection, and reproduction to search for optimal solutions. These algorithms are often employed in optimization problems, where the goal is to find the best set of parameters or configurations. 28. Multi-instance learning. Multi-instance learning deals with datasets where the labels are assigned to sets or bags of instances rather than individual instances. The goal is to classify the entire bag based on the presence or absence of certain features or patterns within the bag. 29. Hybrid approaches. Hybrid approaches combine multiple machine learning techniques or algorithms to solve complex problems. For example, a hybrid approach might involve using clustering to pre-process the data and then applying a supervised learning algorithm for classification. 30. Active reinforcement learning. Active reinforcement learning combines elements of reinforcement learning with active learning. The agent not only learns from interaction with the environment but also actively selects the most informative actions or queries for additional information to improve learning efficiency. In next video, we will discuss about types of machine learning, part 2. Thanks for watching. Please like, share and subscribe.